So hello everyone. So thank you for attending our this week Rutgers Efficient ASM talk. And today we're glad to have the Dr. Adrian Bulat from the Samsung AI Cambridge to give this talk. So Andrea is currently a research scientist at Samsung AI Cambridge. Previously, he received his PhD from the University of Nottingham as part of the computer vision laboratory group. His research work lies at the intersection of the computer vision and machine learning, with work conducted on topics such as the efficient networks, wire-bit quantization, network binarization, and the compression, and the human analysis, where he covered topics such as the phase alignment, phase super resolution, and the human pose estimation. So now let's welcome to Andrea to give us this talk.
Everyone, and thanks for the introduction and for the invitation. It's really a great pleasure to be here today with you. So over recent years, less recently, I guess by now, deep learning has set the state of the art on nearly all fields. Consequently, everyone tries to get a piece of these accurate solutions running on various devices. Here arises a problem, as devices are not made equal and some have less computational resources than others, of course. So this is what I want to talk with you about today, as the goals of today's presentation is to present a solution in the form of extreme quantization and binarization, presenting also some of our recent work that addresses some of the major challenges that such models have, which is mostly about reducing the accuracy drop that occurs when you try to quantize or binarize models. So as I was mentioning earlier, despite their unrivaled accuracy, running state-of-the-art models is slow and expensive in the cloud and impractical due to computational constraint and limited battery life on mobile devices. All in all, the deployment of neural networks faces practicability and cost issues across the stack. So being a long-standing problem, the community, of course, tried to solve it with emerging, and a multitude of directions emerged to elevate this. A few prominent ones that we can mention is network architecture search, where the goal is to identify the best network topology formed by following a set of constraints defined by a user-constructed search space. While promising, the performance is highly correlated with the quality of a search space. Searching with expanding constraints is currently prohibitive, unless, of course, you have a lot of resources. Network compression attempts to either reduce the network size and accelerate its inference by pruning, where the goal is to remove the least important channels, or sparsification, which attempts to learn sparse representation using matrix and tensor decompositions, for example, to exploit low-rank structures. Conditional computing, it's also a promising direction, but generally adjusts the network topology dynamically within a supernetwork, but it can also take various other forms, such as early exiting and so on. And finally, most relevant to our talk today is network quantization, that proposes to perform the operation using data represented on a lower number of bits. So this will allow basically for significantly smaller models and faster inference. In the extreme case, which is 1-bit quantization, also called binarization, all the multiplications in the network, in the convolution itself, can be replaced with bitwise operations. So structure-wise, today we'll touch the following major points. We'll kick off the presentation by setting a few building blocks about quantization, with which many of you will likely be familiar already. Then we'll expand upon this, explaining how all of these techniques change as we move to the most extreme case of quantization, that of 1-bit quantization. With this done, I'll then present 3 recent advancements proposed in our work, but touch and tackle the problem from multiple points of view. So let's get started. So network quantization. Initially, most of the networks used single precision calculus or even higher for training. This is not so surprising really, as on one side, this is what the hardware at the time was natively supporting. And on the other side, there are quite a few problems with fading or exploding gradients, which are making things unstable to train as it was. So really, it was better to have, I guess, something slow that works than something fast that doesn't really train and doesn't give you the right accuracy. In the past few years, as networks become feasible from a commercial standpoint, there was a big push on making the networks work with fewer bits to save costs on one side, and make things run on devices where the amount of computational power permitted by the current hardware technology is limited. Now, why this is a big deal? Well, as you're probably familiar with this picture that shows how numbers are typically stored and consequently interpreted by machines. The typical approach is to use a fixed bit representation or floating point representations, where the latter is more advantageous because it can represent, simply put, more values using the same number of bits. On the quantization side, by now, int8, so using 8 bits, become a standard for deploying models on mobile devices. And it's actually quite impressive that we can restrict ourselves to such a small range where we can represent only 256 values and still retain nearly all the performance. If it's to ignore even the speed considerations offered by this, for example, on a 45 nanometers process, the energy consumption drops from 3.7 picojoules to 0.2 for int8. So we can have massive energy savings that are especially important for devices that rely on a battery to power themselves. Of course, we can do a lot more than this. So if we still look at the extreme case of using one single bit, we can gain significantly we can get significantly faster networks while also reducing the computational cost by order of magnitude. For the network quantization part that we'll discuss, we'll mostly consider the case of int8, since really this is what most of it's of most practical use currently. But the same procedure can be applied, of course, successfully to 2 to 8-bit quantization range. Only the 1-bit quantization is typically more special and requires some special treatment in this sense. So as I was mentioning earlier, int8 quantization is ingrained by now in the current production pipeline. This is a consequence, in a sense, of the fact that we can really quantize them with little to no loss of accuracy. So it's a no-brainer to just take your network, quantize it to int8, and then put it on our device. And you'll basically instantly get 2 to 4 times faster models that occupy 4 times less storage, consume, of course, less power, and so on. And you still maintain most, if not all, of the accuracy of your original network. So how do you perform quantization? Well, firstly, we need to find a way of dropping the number of bits without decreasing the representational power of the model. So let's imagine that we have a bunch of features or filters with values between a minimum and a maximum value. So all of these values between them are represented using single precision. So now what we'll want is to define such a mapping that transform all the values from this range to one of the 2 to the power of n minus 1 states, where n is going to be the number of our bits. Such function that we will call quantizers can largely be categorized into two broad categories, uniform quantizers and non-uniform quantizers. The simplest type of quantizer that one could define is perhaps a uniform affine quantizer. And as its name implies, given a computed scale factor, which is data dependent, that we can see here, we define a set of n equal intervals. In addition to this, we define also a 0 point bias that ensures that 0 is mapped without introducing any errors. Of course, having a 0 point introduces some small inefficiencies on the implementation side. So there are implementations where the 0 point is set to 0. So we have their symmetric quantization. Of course, these scales and so forth can be computed with different granularity. So we can compute, let's say, 1 per channel or 1 per the entire set of channels. So per layer, for example. There are also variants where some additive noise drawn from a uniform distribution is added, and this was shown to increase robustness in certain situations. Now, while uniform quantization techniques are hardware friendly, empirical study has shown that typically the weights of a neural network don't really follow uniform distributions. They typically instead follow long tail distributions, such as the one plotted here, for example, where a big portion of the weights are located around 0, and far away from it, there is really not much going on. So one will ideally like to assign a higher number of intervals, as in increasing the resolution of the interval around the mean, around the center of this. However, uniform quantizers fail to do this because they allocate they allocate equidistant points on the axis. The issue is, however, that if you just try a non-uniform quantizer, where you define arbitrarily small ranges, it's relatively inefficient to compute such function. So we'll also want to have a function that is fast to compute when we quantize the data. One such solution can be given by power of 2 or logarithmic non-uniform quantizers that solve the inefficiency problem by allowing us to perform over quantization using bit shifts, thanks to the fact that they are all powers of 2. So did this solve completely the problem? Well, as you can see here, most of these values now are located around 0 really. So the big issues with this is as we increase the number of bits, we don't really increase much the number of steps far away. So our so at this point, we are basically, as we increase the number of bits, we are overly allocating states near 0, instead of allocating also something for values farther apart. A recent proposed solution to this is the additive power of T quantization, that defines the intervals by taking the sum of 2 n of k bit width terms, also called the base bit width. And as the figure shows, the newly proposed scheme increases the number of quantization levels both in the region close to the mean, but also outside of it, making better use of the entire interval as the number of bits increases. Here we can also see how the intervals are defined for the case of unsigned numbers, but the same can be applied of course, for signed bits. Here we can also see an example with the possible states for b equals 4 and k equals 2. So we can see that we can form, again, 16 unique values using 4 bits. We now hopefully have at least a good idea on how we can map these values from the real domain to the quantized one. And the next obvious question is how we can put this together in practice and train a quantized network. So broadly speaking, there are 2 large classes of approaches, online and offline methods. The offline approaches typically consist in taking a pre-trained real-valued network and quantizing it by minimizing the reconstruction loss between the quantized weights and the real-valued counterpart. So to accommodate for the input quantization, typically a few iterations are made, and such techniques were shown to produce satisfactory results up to int4, for example. As opposed to the above, online approaches either fine-tune an existing network or train it from scratch altogether. In the following, we'll mostly focus on the online case, as really this is what will be more relevant to what we're going to talk next. However, in both cases, the key aspect is how to determine the scaling factor. And for the offline quantization, this has 2 distinct cases, one for the weights, which are fixed and don't change, and other for the input features, which change. So for weights, we can simply compute the mean and the maximum, and then we can determine the quantization parameters for them. However, for the activations, what people do typically is to compute some running mean and average on them using and use them the same. Of course, there are other techniques more advanced for certain situations, but this will basically cover pretty much basics. Now, much stronger, but also perhaps laborious quantization process is that of online quantization that involves training a quantization-aware model that is directly quantized to a target bit width during training. So in order to simulate the desired bit width, we use the so-called fake quantizers that, while working with full precision values, they artificially reduce the number of states as they would have been quantized. So we are mimicking the quantization step, though our values are still real and not quantized in the representation. In practice, basically just means that we apply the quantizers presented previously to the weights and features of the model train time. You may perhaps notice that none of that functions we discuss over good gradients, and the popular solutions to overcome this is to use straight-through estimators, which is typically just an identity function used to compute the gradients, and often it's also clipped to the maximum possible range for that quantizers. Finally, while the forward pass is performed with the values restricted to a desired number of states, we in fact update the real valued continuous copies of the parameters. Note that you also hear about this as this step as called as dequantization. Moving on to network binarization, largely the same core concepts will apply, with a major note that offline quantization is currently not really possible for binary networks. And this will not really result in networks that resemble any sort of good accuracy. So for the case of quantization, given a real of binarization, giving a real valid convolution of input I parameterized by a set of weights W, we construct the binary and the binary weights and the binary features by taking the sign of a real valued version. Since in a binary convolution, both the input features and the weights are binary, this will allow us in the future to replace all the operations with bitwise operations. Unlike normal quantization, where pretty much all the structures are easily quantizable, a layer reordering that moves the batch norms in front of the sign, as you can see here, is a popular approach that generates better performing models. In this case, the batch norm has a dual role. So on one side, it normalizes the data as it will normally do in a network, while on the other side, the bias from the batch norms will effectively shift the data around and change the quantization point, the binarization point, because the sign, of course, will take it's symmetric around 0, and if you shift the 0, if you shift the values around it, of course, we will also influence where the function cuts things to plus and respectively -1. So since binarization preserves only the sign of a signal, but not its magnitude, which is pretty much completely lost, recovering the latter using a per channel or per layer scaling factor is a key aspect for preserving accuracy. There are two main ways of computing its value, using analytical solutions or directly learning it via backpropagation. The analytical form proposed by Rastigari et al. In the XNOR.NET paper computes a different scaling factor for the weights and for the activations. However, the later one for the activation is typically ignored and not really computed, as it requires to be recomputed at every pass. And this can get expensive when we're talking about binary networks. Now, while the analytical solution works well, it generally fails to take into consideration the overall task at hand and has limited flexibility. More recently, in a subsequent work, we proposed to compute it discriminatively, learning it via backpropagation, and instead of learning alpha in such a way as to minimize the local reconstruction error. In this case, we train it via backpropagation in an attempt to minimize the error with respect of a target task. And now, while the scaling factor is computed as a one value or one value per channel, we go beyond this and we also experiment with computing it per every dimension of the channels. So in a case of a three-dimensional set of weights, we can compute a vector for every dimension. Note that at this time, we can simply merge them together into a single scaling factor, so we can avoid an increase in computation. Note that the operation between the features and the scaling factor is an element-wise multiplication. Right, so we saw previously that for the case of quantization, the derivative of a quantizer is typically approximated using a straight-through estimator, and a similar approach needs to be taken here. Sorry. As we can see, the derivative of a sign is uninformative and cannot be really used during training, as it's really just a spike. The most popular and computationally cheap approach is to use the derivative of a hard tangent or the clip function, which is in the range -1, 1, which clips things in the range -1, and 0 everywhere else. Of course, multiple alternatives were tried with various degrees of success beyond this. A few noteworthy ones are using the tangent, soft sine, or various polynomials. Some more recent approaches also attempt to define this in a dynamic manner based on the data itself. So, given that binarization is intuitively difficult, why do we care? Well, binary convolutions can be up to 64 times faster and 32 times smaller on a modern x64 CPU. And such networks outperform in terms of efficiency by far any other types of network compression or quantization. Not only they are faster, but they can also lead, of course, to improved battery life, smaller application packages or update packages. And thanks to their binary nature, we can implement them, as I was saying earlier, using bitwise operation. A simple example is offered here using the CMD concept, which means single instruction, multiple data. So we're basically packing, let's say, 32 binary values inside a single float, and then we operate using that float. So basically in one go, we can do 32 times operations, having a significantly higher throughput for our computation. Of course, there is no free lunch. So training binary networks to satisfactory accuracy remains an open problem, with current work attempting to reduce the accuracy gap between a real value network and its binarized counterpart. Most of this difficulty arises from the discrete nature of the binarization, with gradients being often uninformative, but can either fade or explode. There's also high sensitivity to distortion, since small changes can make the jumps between the two states. As we perhaps got hinted during the layer rewarding part, the exact topology of a network is important for binarization, as not all architectures are easy to binarize. So how does architecture impact binarization? Well, the first major point is that no matter the architecture, over-parameterized models will, of course, fare a lot better under extreme quantization, as they have a higher reserve capacity in a sense. Secondly, as the number of unique representable configurations for a given network is small in comparison to a full precision model, the amount of information that is carried out throughout the network is limited too. So a direct way of increasing this is by simply making the networks wider. In a sense, binary networks favor wider architectures over deeper ones. Of course, which is not to say that both wider and deeper networks are not better than shallow ones. Thirdly, certain layer configurations, such as depthwise convolutions, are problematic to train due to what is called the double approximation problem, where the depthwise convolutions already are a direct approximation of a normal convolution network. As a consequence, it's unlikely that you will be able to binarize the mobile net with much success, unless you add some real-valued operations in it. And fourthly, due to the decreased information flow and the poor gradients, more skip connections will almost always help. There are, of course, more cases to consider beyond this point, but this probably sets the state and paints a clear picture already, probably. Now, manually searching for an easy-to-quantize network is a laborious process, and as such, recently, we propose of the first adoption of neural architecture search for binary networks. Firstly, we show that directly applying NAST, the binary domain provides poor results. And to elevate this, we describe 3 key ingredients for successfully applying NAST to the binary domain. Specifically, we introduce and design a novel binary-oriented search space, since we were mentioning that search spaces are really important. Secondly, we propose a new mechanism for controlling and stabilizing the resulting search topologies. And third, we propose and validate a series of new strategies for binary networks that led to faster convergence and lower search times. And all in all, this will basically help us set a new state of art for binary networks on CFAR datasets and ImageNet when we tested it. So as I was saying, one of the key components that make NAS successful is their constrained search space. Its quality being often a determining factor on how good the search architecture can perform. Since searching across a large space is computationally prohibitive, most often the recent NAS methods manually define a series of opt operations known to produce satisfactory results when used in handcrafted network topologies, which are basically 3x3, 5x5, and 5x5 dilated convolutions, and the same with separable convolutions plus some max pooling, average pooling, and then the skip connections. There's also a zero skip connection, which means there should be no connection here. We know that for the real value networks, a random search performed on the aforementioned space on CIFAR10 achieves already a top one error of 3.29 versus, for example, a 276 roughly for second order Dart. So we have a very small gap between what a search can do on this search space and what a randomly sampled network can do. So this shows that really the search space is one of the key that will give you a very good result. However, not all operations used for real valued case are suitable, as we were saying. And in fact, we found that using the standard Dart search space and searching the binary domain does not really converge most of the time. This is due to the presence, for example, of depth-wise separable convolutions and so forth. Furthermore, the one-by-one convolution layers and the bottleneck blocks were already shown to be hard to binarize because of the feature compression, and there are quite a few one-by-one layers here present, at least via the separable convolutions, which further make things harder to train. So we propose a new search space constructed from a binary first point of view, which avoids the aforementioned shortcomings. And while we preserve the zero identity connections alongside the pooling layers, which do not really contain learnable parameters or binary operations, we propose to replace the convolutional operations with a few new ones. So basically, we're going to use grouped convolutions and dilated grouped convolutions, moving away from the extreme case of a separable convolution. This will also remove in the process all the one-by-one convolutional layers while maintaining the search space similar. And when we switch to this and do a search on binary networks, the gap itself widens to 1.2% between a random search versus something that our method will find. So we know that also that due to the gradient mismatch, exploding or vanishing gradients are more likely to occur, since we mentioned we pretty much estimate the gradients using some straight-through estimators. Now, to improve this in all convolution layers, the depth of all operations used is set to 1, meaning that we use one convolution operator per layer as opposed to 4 convolutions for 2 depth-wise separable used in Dart, for example, which facilitates learning for binary networks. Another consequence of using operations with a depth equal to 1 is a latency improvement due to effectively shallower network. Finally, in order to improve a gradient and the information flow, which is even more critical, we also add the skip connection around every operation. So every operation will be wrapped around 1 as well, as shown in the figure. Now, despite its success and appealing formulation, Dart's accuracy can vary widely between runs, depending on the random seed. Often it can collapse to a degenerate solution that contains mostly skip connections. While there are various heuristics proposed to elevate this for real-valued networks, we find that most of them are suboptimal for binary networks. And furthermore, given that during search, the input of a node is obtained by taking a weighted sum of all the incoming edges. In order to maximize the flow of information, the architecture parameters tend to converge to the same value, making the selection of the final architecture problematic and susceptible to noise. This results in topologies that may perform worse than a random selection. The binary search, even default configuration, further tries to cheat really by making use of a few real valid operations present, such as max pooling and the skip connections. So to alleviate the aforementioned issues and encourage the search procedure to be more discriminative, forcing it to make harder decisions, we propose to use a temperature factor T lower than 1. So this has the desirable effect of making the distribution of architecture parameters less uniform and making it more spiky and more discriminative as such. Hence, during training, because of information streams are aggregated using a weighted sum, the network cannot equally or near equally rely on all possible operations by pulling information from all of them. Instead, in order to ensure convergence to a satisfactory solution, it has to assign the highest probability to a non-zero op, enforced by subunitary temperature in this case. This behavior also follows closer evaluation procedures where a single operation will be selected in the end, reducing as such the performance discrepancy between the search, where the network pulls information from all paths, and evaluation when a single path has to be selected. How the distribution of the layers vary as we change the temperature. So we can see for lower temperatures, we have significantly larger number of convolutional operations selected, as opposed to previously where the network was favoring skip connections. Since binary networks are harder to train, we propose to perform the search by only binarizing activations while keeping the weights real-valued. Such models correlate well with the performance of the fully binarized networks while being faster and easier to train. Of course, during evaluation, the networks will always be fully binarized. So overall, our approach is capable of discovering high-performing binary cells, offering new or validating existing insights about optimal binary topologies that help draw some important conclusions. As depicted, the cells found tend to prefer convolutional layers with larger kernel sizes, such as 5 by 5, which help alleviate the limited representational power found in such networks. In addition, to preserve information flow, a real-valued path that connects one of the input nodes to the output is pretty much always present. Furthermore, since the downsampling operation compresses the information across the spatial dimension, to compensate for this, the reduction cell tends to be wider, as in more information can flow through when the resolution decreases, as opposed to the normal cell, which generally is deeper. Here we can see some results on comparing our method on CFAR10 with some other network architecture search. As you can see, we perform noticeably better than all prior works when applied to binary network search. And we can see similar results on ImageNet2. So the architectures found earlier not only perform better, but they also allow us to get a further insight on how binarizable network structure should look like. One major hurdle that we keep trying to solve in all of these endeavors is increasing the representational capacity of such models without increasing the computational cost. One direction that we explored in our recent work, published at ICR 2021, is that of conditional computing for binary networks. The core idea is to learn a set of binary weights that will specialize themselves to certain components of the data without extra supervision. As such, by trading some space, we could increase the representational capacity of the binary networks. Our proposed expert binary convolutions consist of a gating function, a set of expert weights, and the convolution operation itself. The gating function is implemented using a small linear layer, followed by a winner takes all activation that selects a single binary expert out of a given set. Now, the derivative of activation is adapted such as that all weights will receive gradients during training, even if they are not selected. So it will behave basically as a winner takes all or an argmax function, if you prefer, during forward pass, and it will take the derivative of a softmax during a backward pass. Now, note that unlike prior works for real-valued networks that select the top K, where a linear combination of experts, which is not feasible for binary networks, has any further interactions after the selections, will either break the binarization or introduce extra computational cost. On the right, for a model with 4 experts, we can see that the network developed preference for certain classes of an object, evidentiating the effect of a multiple experts. Note that since the gating function is very light, the additional number of flops introduced by this selector is insignificant, as it really just maps, let's say, 256 channels to 4 values in this case. Now, due to the discrete decision-making process early on, the training can be unstable. Therefore, to stabilize the training, we firstly train one single expert, and then we use this to initialize the training of all n experts by really expanding it over the rest. This ensures that early on in the process, any decisions made by the gating function is a good decision. Overall, our optimization policy will lead to significantly better networks. And in fact, without it, in many of the cases, it will not really converge to a satisfactory solution, as the network will have problems in deciding which expert should be assigned to which data. Not that there is no other supervisory signal to point the network what data should be assigned to what expert. So this is done completely unsupervised for this part. So here we can see again some results on ImageNet, where we improve by more than 5% without increasing the computational power. These results also include some other architecture adaptations. So the actual gains from the conditional or expert binary convolutions is more like 2 to 3%. But if you want to see also the other architectural changes, which mostly are lessons drawn from our previous work, where we try to find them automatically, you can see them in the paper. So while all of these methods presented until now offer great accuracy speed trade-offs, on one side, appropriate hardware implementations are required, and on the other side, depending on the device, some computational resources may be wasted, as the network will really require the same amount of computing power. However, the devices that you deploy it on may have more or less than that. In general, this is a problem that the community tries to solve. Because as the number of devices increases and their computational power changes, different models are now typically required to fully utilize the resources without compromising the quality of the responsiveness of the application. As such, researchers and developers are faced with the problem of creating and then maintaining device-specific models. If it's to look within the framework of quantizable networks, one way of adjusting the ratio between speed and accuracy is by changing the number of bits. Generally, up to some point, one can trade speed for accuracy, and vice versa by allocating more bits per network, block, or layer. This is what we explored in our recent work, but with a major modification. Our proposed approach creates networks that can change their bit width at every block at runtime without extra training, such as to allow the same network to be suitable for multiple devices at once. And then, depending on certain developer-imposed conditions, the network can change on the fly the quantization of each block. So why not quantize them offline, you would say? Well, for a high number of bits, post-training quantization is feasible, so one can just take a model and do an offline quantization in a few minutes and get the new models. However, for low bit quantization, which will mean really here 4 bits or lower, this will require training-aware quantization, so this will not be possible any longer without retraining the network to a specific bit width, which cannot be changed thereafter. So if you train your network to work with 3 bits, then if you wanted to work now with 2, you'll have to fine-tune it again with this new target in mind. Now, given that different hardware has support for different quantization levels, and the existing accuracy speed trade-offs were lower, where lower bit networks are faster but less accurate, it's not uncommon to require the quantization of the same network multiple times. As such, a current paradigm for training models with different quantization levels consists in running the training procedure n times, producing n quantized models. Not only such approach results in higher storage requirements, but it also involves longer training times as inflexible. More recently, in other bits, the authors alleviate the storage issue by training a model with n quantization levels and shared weights. However, the network is limited to the same bit width across all layers. So if we have, let's say, 4 possible quantization layers, then we have also 4 possible networks that other bits can offer. Now, what if we could define the quantization level instead at a layer or a block level, adjusting in real time the network accuracy and speed depending on device, battery level, or various other factors, including how difficult an image is, perhaps? To this end, we deviate from the common paradigm and introduce the first network with granular bit width selection at runtime, Unlike prior work using a single shared set of weights, whose size is defined by the highest bit weight at runtime, our model can select arbitrary combinations of different bit weights, allowing for an easy and fine trade-off between accuracy and speed, without affecting at all the overall network's ability for highly accurate networks or for very fast ones. In summary, our main technical contributions on this are in order to properly compensate for the distribution shift that arises when a change in the bit width occurs between two consecutive layers, for each transition between different bit widths, we propose to run a separate batch normalization layer, coined transitional batch norm. Traditionally, different quantization schemes were used for 1-bit quantization and respectively for 2-bit and higher, and to facilitate the training, unify them under a shared common formulation. This change also enables us to quantize the weights without using the full precision copy, instead relying on the B+1 quantized version for a bit width target quantization. So for example, if we have 1 to 4 bits quantization, the maximum storage of the model is going to be taken by the 4-bit quantization, and then we can obtain the 3 and 2 bits and so on by just applying a function over the 4-bit version or over the 3 one and so forth. Now, since training such network is non-trivial, we devise a specialized training strategy that allows the training of such meta networks. Finally, since not all subnets are identical in performance, even if they have the same cost, we propose an offline selection procedure to identify the most promising subnetworks. This can also be treated as a near zero cost network search in a sense. So our unified quantization scheme attempts to address two prevalent issues. Firstly, different functions and formulations are used, as I was saying previously, for 1-bit and n-bit quantization. The n-bit quantization is typically performed using round operators, followed by a scaling function that maps the values between 0 and 1. In contrast, the binarization is performed using the same function, but operates on the plus and minus 1 range. Secondly, quantizing the n-1 requires a full precision weight, since the levels between quantization levels don't necessarily align, as is shown in the leftmost figure. As such, instead, we operate directly on the minus m to plus m range for the quantized types, using a floor function that aligns the quantization levels as shown in the rightmost figure. Note that in practice, we opt for asymmetrical quantization that results in 2 to the power of b minus 1 states. This, for example, for b equals 2 will degenerate in what is known in literature as ternary quantization, as we'll have only 3 states instead of 4. So we can ensure that symmetricity. For reference, we're also showing the center of a quantization mapping used in AltaBits. Now, quantizing the individual layers and blocks for different bit weights will result in features that follow different distributions. It is because of 2 main reasons. Firstly, it's a consequence of an inherent change in the representational power due to the change of precision. And secondly, as the number of bits drops, the network is unable to approximate closely the future distribution of a higher bit weight. As the weight distribution significantly changes, to properly compensate for this, for each transition between different bit weights, so let's say if a layer transitions from 1 bit to 2 bits or vice versa, we'll learn unique specific set of affine parameters for our batch norm layer. We note that introducing the transitional batch norm layers does not induce any increase in computational complexity of a network, as only one of them will be active at a time. There will be, however, a small increase in the network size. However, this is typically less than 1% of a total parameters count. Importantly, I also want to emphasize that without the transitional batch norm, the network is unable to converge to a satisfactory level of accuracy. Notice in the figure the reduction in error before and after applying the transitional batch norm. So you can see that this has significantly lower average variance. A key remaining aspect is how to train the proposed meta network, which turns out to be very challenging for several reasons. So if you take a direct and naive approach where all the paths are active simultaneously, it's unfeasible to do this due to memory and computational constraints, as we'll have to keep into memory too many variations at the same time. And besides this, we considered an approximation to this by training all the paths between the two adjacent layers. However, even in this case, we found the models unstable to train due to the internal competition that arises between them, especially early on in the training. A more computational feasible approach is to select randomly with equal probability during training an active subpath or a set of active subpaths. However, in our experiments, we found this leads to networks in which the accuracy of all bit weights are closely tied together. So this doesn't really work. And they pull all the accuracy to the accuracy of the lowest bit weight. However, so in order basically to successfully train such networks, we introduce a quantized meta network that during its training procedure, that adopts a multi-stage training procedures, where at the first stage, we just warm up the network without mixing any data and keeping the activations full precision. So basically what we'll have is a network that quantizes only the activations and keeps the weights real value. Then during the second stage, we will quantize each network independently. So at this stage, what we'll have is a network that will be capable to have the same bit width across all layers. So let's say if our target is to have 1 to 4 bit quantization, so 4 values, then we'll train our network to be quantizable to 1, 2, 3, and 4 bits. Finally, we will gradually alternate between selecting a random subpath and selecting a network that has across all layers the same bit weight. So basically, this will allow the network to gradually adapt from having the same quantization level across the entire network to have different randomly selected quantization bit weights at every block or layer. Now, the bit mixer trained meta network contains an exponential number of subnetworks. By changing the bit width of its individual layer at runtime and without extra training, a device or an application where the network is deployed can benefit from a finer trade-off between accuracy and speed. However, as I was saying earlier, not all networks are created subequal, and we need to somehow identify the most promising candidates. This can be viewed as a post-training network search. To facilitate the selection of interesting networks as measured by accuracy per average bit width, candidates of a given population, for each layers, we compute the top eigenvalue of a Hessian. For this purpose, we use the network with the highest possible bit width for the computation of eigenvalues. In general, smaller eigenvalues correspond to flatter loss surfaces, which in turn suggests that such layers are good candidates for more aggressive quantization, given that the induced errors are less likely to be amplified. Then, given a target cost, we generate a set of candidates using a greedy approach and rank them accordingly to the cost computed by the eigenvalues. The best models are then selected and evaluated. On the right, we can see a few subnets plotted out of a single model. So we can see that as we change the bit width, the network performance varies smoothly. Again, all of these data points are from the same set of weights that dynamically change the quantization level at runtime. Since our method is the first one of its category, there is not really a direct comparison. However, we compare here with a few models that define the number of bits at train time. So for example, EDMIPS EDMIPS uses a NAS approach for this, while AdaBits is the method that we mentioned earlier. So now that our method offers competitive results, despite being significantly more flexible. So we are pretty much near the end of our presentation. So if you are interested in playing with binary networks, I have a micro library that can help you do this, that you can find it here, which will make things quite easy to binarize. So this is a simple example of how you can achieve this. So all you have to do pretty much is to take your model and pass the desired configuration that defines what type of quantization you want for activation, what type for your weights, and what types of post-processing you want, and then it should be able to help you generate binarizable network. Okay, thank you. And if you have any questions?
Thank you. Very interesting talk. So any questions from the?
Yeah, hi, Professor. Hi, Adrian. This is Vivek. Very interesting talk. I'm sorry you would have covered it, but if I can request you to kindly explain the analytical part in one of the slides where we were talking about the discriminating and the analytical process. If you could explain that analytical part, how did you arrive at that equation? And if you could talk about a little more about that, it would be helpful.
For binarization, you mean?
Yes.
So this one, I guess?
Yeah, this one, yes.
So these equations are obtained by solving an equation system where the target is to minimize the discrepancy between the real valued weights and the binary ones. So if you solve that equation system, you will obtain that an optimal scaling factor for which the error is minimized can be computed by taking the absolute of the average values per that channel. So that's what is going to compute for each channel. You're going to take the average. So you're going to take the average of absolute values. Yeah. While for the activations, you solve again the same system. However, this time, because every time you run the network, the activations changes. You have to compute the same every time. So this is an efficient derivation of that process, which basically means that you will take the average across all channels. So you'll obtain a map which is the same as the resolution of your image. So let's say width times height. Then you'll create a kernel, which is going to be of the same size as the kernel of your convolution. And you're going to fill with values that are 1 over k squared. So in this case, let's say if you have a 3×3, then you will fill this kernel with 1 over 9 as a value, and you'll perform a convolution of this kernel over this this input, and then you'll obtain again a set of per pixel this time scaling factors that you'll multiply to the features. However, this, as I was saying, is not really computed used in practice much. And the main reason is that it's relatively expensive to recompute them for every forward pass. If you want to see the full equation derivations, you can check the XNOR net paper, which is this one, by Rastegari, if you want to check the exact equations for this. But it's the main gist. But we're solving them on an equation that tries to minimize again the error of reconstruction errors after applying the sine function over the real valid weights.
Yeah, thank you so much.
Other questions from the audience?
Hello, I have a question.
Hello, yeah.
Oh, okay. When I apply the binarization on mobile now V1 V2, I met a question that the training is cannot converge. So do you have any good suggestion?
So as I was saying, at some point, the main issue with this is really due to the separable convolutions. So I saw a few works that are trying to kind of address this in some sense, but what they primarily do if I remember correctly, is that they basically used real valued weights or int8 quantization for the separable convolutions. So really, it's a question of capacity in this sense. The separable convolutions are already very compressed, so squeezing them more and compressing them further is quite challenging. So as far as I know, the best methods are that try to binarize them, get around 40% or something like this top on accuracy on ImageNet, which is quite low. So if you really have to use MobileNet, you likely have to use a higher level of quantization for that particular layer, so for the separable one. So you could go, I don't know, with 2 or 3 bits quantization, so to get something in between. But as far as I know, quantizing them directly doesn't really work currently. I don't know, does this answer your question? Or do you have any follow-up?
I think he's mute. Okay, that's fine. So other questions from the audience? So if the audience don't have some other questions, actually I have several questions to ask. Yeah. So so very what I want to say is first very interesting talk and condensing any informative idea and knowledge about the quantized network and binary network. And my first question is that I remember in one of your slides you mentioned that the several factors impact the architecture design. I think that is in the NAS for the binarized. Yeah. So here, so the third point, so reduced number of the state will favor wider networks. So does that mean that so when we go for the lower precision, so for the overall topology network, so it's preferable to use the wide network instead of the deep network. So is there any kind of the explanation for this phenomenon?
So one simple way to look at it is on how much information can go through the network. So let's say if you have binary states, right? You can have only -1 and 1, so 2 states. Now let's look at the 3x3 kernel, right? So again, your number of states is relatively small in comparison with a normal one. So we have now 2 to the power of 3, right? Unique states and so forth. So the number of unique states that you can represent on a given surface, let's say, so on a given number of pixels is quite limited in practice. Now, if you still look at the number of channels, so basically increasing the resolution is one way of improving your accuracy, and the other way is increasing the number of channels, with the whole goal of having more unique configurations formed with -1 and 1 values. So the wider the network is, so the larger the amount of channels, the more unique configurations you can possibly represent inside the network. So you can have more information flowing towards the end of the network, which is quite noticeable also on how then decreasing resolution is done. So one thing that people notice when we're binarizing ResNet, for example, is that a lot of the performance were lost during that average pooling that was decreasing the resolution and increasing the number of channels. So what people went for was to either have a real valued 1x1 convolution there for the decrease in resolution, or to double the number of channels during the decrease of in resolution. So instead of having, let's say, C channels going to instead of having W over 2 resolution, that goes instead of having W into W/2 resolution and increasing the channels twice, they expand the channels before the decrease in resolution. So the decrease in resolution happens at an inflated level, right? So you don't decrease the resolution and increase the channels. You first keep the resolution, double the channels, and then do the downsample. So again, all of these things kind of point out that really having a wider network that allows you to pass more information is benefic, which is also what we observed when we switched from to wider architectures. And one easy way of doing this is really by using grouped convolutions. So you increase the number of channels, but you still kind of maintain a number of flops constant.
Thank you. And I was also wondering, so does that also imply that, for example, for the low precision network, so the gradient, the flow of the gradient in the backward propagation, so maybe that is kind of the more difficult. So that's a potential another reason why we choose to go for the wider network instead of the deeper network.
Yeah, that definitely contributes too. So this is why, for example, having more skip connections helps quite a bit. So for example, in bireal networks, the change proposed there by the authors was to add a skip connection around every convolutional layer, and this gave, I believe, 2% or something like this. So definitely fading gradients are more of an issue. So you can either indeed have this more shallow networks that are wider, where you can try to compensate with skip connections or really try to do both. So definitely.
Thank you. And another question, I think that is on your next slide. Oh, sorry, next, yeah, this one, yeah. So here, so you mentioned that in this slide show that, so it looks like the group convolution is preferable when we do the NAS for the binary network. So is there any kind of the explanation for that? And also, so here your proposed search philosophy, it is also still based on the differentiable NAS or something else. So, and if you using the differentiable NAS, so I was wondering whether like some other type of the NAS, like the SuperNet with sharing NAS, whether that is can be such philosophy can be used as here as well.
Yeah, there is no reason why other type of NAS shouldn't be applicable to this. At the time we tried this, when we started, I think the first super NAS-based approaches were still not out yet, but really there is no reason why any NAS couldn't be applied on this. Because really, from what we saw at least, and what the literature seems to point out, having a very good search space is pretty much the key ingredient, since it basically avoids you, it prevents you from failing. So even if you kind of fail in your search, if your search space is very good, you'll still get some very good results. So it should really be applicable not only to differentiable, well, not only to Dart-based approaches, but also to any other types like the SuperNet or the SuperNetwork ones, like the one, the ICR paper, which I can't really remember now the name, but yeah.
Yeah. So then, how about why the group convolution or the group group convolution is instead of the depth-wise convolution is preferable here for the binaries?
So the issues with the depth-wise convolution is that the number of, so in a separable convolutions where depth-wise convolutions, for the convolution with a kernel size higher than 1 by 1, so let's say 3 by 3, the number of groups is equal to the number of channels. So you have an extreme, which is basically equivalent with an extreme matrix decomposition. So you are compressing the data quite a bit. So this is why it's really hard to compress further something that was already compressed. So you're pushing things to a very limit at that point. While for a group convolutions, you can define a reasonable group size, such that you are still able to approximate it. Well, you allow basically for enough freedom in the weights to learn something that is binarizable. Because if you start with something that is applied to only one channels, really there is not much freedom, especially given on how the binary convolution works, like which is pretty much pass-through filter. So if it's -1, let's say, you allow for something to pass, it to not pass, and if it's 1, you allow it to pass.
Okay, I think this is a very interesting observation and hypothesis. Yeah, it kind of connects the topology of the neural design and the quantization.
Yeah, plus the reason again of why not using normal convolutions is very so the goal is if your goal is to increase the width, then doing so with full convolution is very expensive.
Yeah, and my last question, yeah, that is on your bit mixer.
Mm-hmm.
So in that work, so actually I think it's a question from the audience. I think you can respond in the chat box. Can you see that question?
Yeah, so you can do this either by adding more options. So you can do this, let's say, in a discrete fashion, by adding multiple options, even for darts. So let's say you define with 4, 16, and whatnot. You can do this, so this sounds expensive, but it's not so much because the search is done anyway on a micro network where the width of the channels is anyway a lot smaller. So you can do either this, or you can sample them using some sort of reinforcement learning techniques. So in our work, we did it with darts, but it should be doable also with some reinforcement learning, where you should be able to select the group size with a better granularity, perhaps.
And I was also curious about how about the GPU hours you need to search for the binary net.
So it's not that much. It's only a few hours on a single GPU.
Okay, that's pretty fast. Yeah.
But again, it's because it's done in a proxy manner. So you don't directly search, let's say on ImageNet, you search on CFAR and then you scale it up. You could do this directly on ImageNet and you probably get slightly better results, but yes, then this gets indeed a bit more expensive.
Yeah. Yeah.
So I guess this is why people kind of moved a bit to SuperNets, where they can train it directly on the target data set and probably get better performance from that.
Yeah. And my question on the bit mixer is that so here your quantization and activation, that's kind of reconfigured. And I was wondering, so how about the computation itself? So it is also kind of reconfigurable, or will it still be converted when we do the practical implementation? We still need to convert it to the floating point implementation and then use the GMM to do the floating point GMM to do the computation.
You mean during training or during deployment?
Both.
So during training, yes, we use full precisions. So we use that fake quantizer thing where the weights are actually real valued, but we pretend that they're quantized by applying that functions and restricting their possible values. During deployment, you'll probably need, well, you'll basically need, of course, some implementations that can work directly with that values. However, the switch between the quantization levels, let's say for the weights, are very cheap to do. So you basically just run a round function. So obtaining that values is cheap. And you can, of course, run them at their native bit width. But again, to run them at native bit width, you need some custom implementations. You cannot use off-the-shelf frameworks. So they won't be able to do this. As typically, they either do up to int8 only, or they will not be capable of switching dynamically between different bit widths. So yeah, custom implementation.
Okay. And also for this, the reconfigure bits, so it is reconfigurable also includes those the odd numbers or just the even numbers, 2, 4, 6, 8, or also includes the 3 bits or the 5 bits.
We experiment with 2, 3, 4 bits, so 1, 2, 3, 4.
1, 2, 3.
So it includes exactly. We didn't really go for more than this because really the performance of int4 or int8 is so close together that there is not really much point, I believe, in exploring this gap. when you want to have actually some smoothness. So 0.5%, let's say, or 0.3 difference between the two is not a major enough gap to justify such a network. However, the gap between 4 bits and 1 bit can be quite large depending on the architecture. So there is much more room and reasoning to actually have something that transitions smoothly, as we could see in this figure here, where you can see that 2 bits basically are at 64, let's say, accuracy, and you can, as we increase the average bit width, where the average bit width is computing by taking the mean of the bit width of every layer, right? You can see that this very smoothly, but as you approach 4 bits, it really saturates. So this why there is not much point in going beyond that.
Yeah, that makes sense. Yeah. Thank you very much. So, any other questions from the audience? Okay, so if no more other questions, so let's thank our speaker again for this very wonderful talk. And also, so this talk is also the last talk in this summer series of the Efficient AI seminar. So our full series of talk will be announced soon. So again, also thank all the audience to attend our talks today, and thank you very much. So thank you.
So much for our invitation.
Thank you. Have a wonderful day.
You too. Bye.